Hello and welcome one and all. In this session, we will revisit Dagster. We will talk about changes to this workflow orchestration system due to recent updates. Dagster is an orchestrator that's designed for developing and maintaining data assets such as tables, datasets, machine learning models, and reports. In the previous video, we created a Dagster project using Dagster version 0.15. In that project, we converted our Python ETL data pipeline to a Dagster compatible code. In doing so, we covered main Dagster concepts such as op, jobs, and schedule. And we brought the various components together in a repository module. Much has changed since then. So we will create a new project and review its structure. We will cover software-defined assets, as Dagster is pushing towards software-defined assets. Finally, we will store the outputs of the assets or the data pipeline into a permanent storage for later use. By default, our pipeline outputs are stored as pickle file in the Dagster home folder. What if we want to store the outputs in a database table or in a readable file format such as CSV or Parquet? Previously, we pushed the data to a database via custom Python script. However, to push data to a file system or to a database, Dagster has input and output managers, simply called IO managers. These enable us to read and write data to storage systems. Using IO managers, we can save the outputs in a file system or store our data as tables in a database. They manage the input by reading an asset from where the data is stored and load it into memory to be used by a dependent asset. We will define a file and a database IO manager. Let's check our environment and see the available Dagit and Dagster versions. At the time of the recording, we are working with version 1.3.1. The command to create a Dagster project in the previous version was Dagster new-project, and this was followed by the project name. This was the supported command in the version 0.15. However, in the new version 1.3.1, the command to create a new project is as follows: Dagster project, and we have a keyword scaffold, -- name, then the project name. So we will provide Dagster project scaffold -- name ETL. Let's review the project structure in this version. As you can see, there is no workspace.yaml file. It is replaced by a pyproject.toml file. This sets up the reference to our ETL directory that houses the code. Inside the ETL folder, we only see two files: init and an asset file. In the init file, we import all of our assets and define the jobs and schedules here. This allows Dagster to load our assets and jobs. As our project grows, it is recommended to organize assets in subpackages or submodules. Just like in the previous version, we can create folders and move our code inside those folders. In the assets file, we define our ETL logic. This is a very minimalistic setup, just the base required code to get you up and running. We will develop an ETL pipeline with Dagster software-defined assets. We will ingest data from external sources, explore and transform that data, and then materialize the output that we can consume later. Let's start by defining what are software-defined assets. A software-defined asset is an object in persistent storage. It can be a database table, a file in our file system, or a file in S3 storage, or a machine learning model. Software-defined asset is a declarative approach to data management, meaning we write the code that a product table should exist in AdventureWorks database and how this table should be computed. A software-defined asset can be referenced by an asset key. An asset key is a handle for referring to the asset such as a file or a table. In addition, an asset has a set of upstream asset key. This is a pointer to the previous asset that helps derive the current asset. For example, if you have a source table, the current table will have a pointer to the source table so it can read data from the source and then build the current table. We will see an example of this in our project. Now that we have a project created and we know what assets are, it's time for us to build the first part of our data pipeline. Before jumping into the code, let's install the required libraries in our virtual environment. We have the libraries listed in our requirements file. We will execute a pip command with -r and provided our requirements file. This will go ahead and install the required libraries. We will borrow much of the code from the previous session. We still need a database connection to extract data from the source. In the previous session, we defined a db_conf file. We'll copy this file in the current project, and we will save this in our resources folder. In this file, we only keep the SQL Server connection. This is our source. We will handle our target, Postgres, via IO Manager. Let's open the assets file and start defining our assets. We can change the name of this file to something appropriate. For example, we can give it the same name as our table. As we build more assets, this will help us distinguish between them. Things can get quite complex if you have hundreds of files. We will rename this to assets_product category. In this file, we import assets from Dagster and get SQL_conf from the db_conf file. And we are importing this file from the resources folder. We will use pandas to read and transform data. And finally, we'll import logging to log some information about our data. We begin with asset decorator. Under this, we define a function that will read data from the source. We provide a name for this function, extract dim product category. This function takes context as an argument. This is a special object and it exposes Dagster system API resources, access and logging. We can use context as the first argument of a compute function. This is followed by the type of return value from this function. It will be a data frame, meaning this function will return a data frame. We call the getSQL_conf function in a with statement. This gives us access to the SQL Server connection. We utilize the read SQL query function from pandas and pass it a SQL statement along with our connection. This returns a data frame that we save into a df variable. Finally, we return this variable. This completes the extract function. In our virtual environment, let's go ahead and launch Dagster UI with dagget command. In the UI, we can interact with our asset. We will execute the asset and see it materialized. We will see the default IO Manager in action, and this IO Manager writes this file to our Dagster home location. The Dagster home is set via environment variable. We can copy the location of the file and view it. By default, the outputs are stored in a pickle file. We can read the pickle file with pandas if we want to review the output. Anyways, let's make some update to our asset. Let's add some tags to it. So back in VS Code, we assign a group name to this asset. This way we can group the related assets together. In addition, we can add a compute kind of pandas. This will display the return type of this asset in the Dagget UI. We also log the first 5 rows of the data frame, so we get a preview of the data. With these changes in place, let's save our file and reload our asset definition in the UI. We see our group name in the left pane, and below the asset we see a pandas tag. This tells us that this asset returns a pandas object. We materialize the asset, and this time around we get a preview of the data frame. Okay, we have our extract part of the ETL pipeline. Let's go ahead and define our first custom IO manager to change the persistent storage for this asset. We will change the output of this asset from a pickle file to a CSV file with a custom IO manager, so we can open the file in Excel and review it. If you're working with a larger dataset, then you can convert your asset to a Parquet file. We will create an IO folder and put our IO manager file here. In the future, if we need to add more custom IO managers, they will be saved in this directory. In this folder, we will create a new Python file. I will call it file_io. In this file, we import the required libraries. We start by defining a class called local file system IO manager, and this takes IO manager as an argument. Under this class, we define three functions. In the first function, we define the path of the file. The first argument is self. Self represents an instance of the class. By using the self, we can access the attributes and method of the class in Python. It binds the attribute with the given argument. This is followed by asset key. If you recall, an asset key is a handle for referring to the asset. And the return type of this function will be a string. We declare a variable, our path. With the help of join function, os.path, we combine a folder location with asset key and append the extension, which is CSV. So this is the makeup of our file path. Let's create the warehouse underscore location and the subfolder inside it in the root directory of our project. It will be under the first ETL folder. We create a warehouse underscore location folder and inside it a result folder. The output of our asset will be stored here. Back in our code, we return the absolute path of the current working directory with file name. The second function saves the output of the asset. In this function, we pass the context and the data frame along with self. We call the first function to obtain the file path. We log info for the UI and finally save the data frame with to_CSV function. In the last function, we get the file path and read the file into a data frame and return this data frame. Finally, we define a function that returns this class. We convert this to IO manager with IO manager decorator. So this is our custom IO manager that handles the output of our asset. Let's implement this in our code. In the asset, we define an IO manager key and set this to a value of file_io. In the init file, we import from IO file IO module. In the definition, we define resources and set the key value for IO manager. This must be the same value we provided in the asset. We set this to file_io and call our class from this module. Our custom IO manager is implemented. Let's save all the files we have touched and head to Dagget UI. Let's reload our asset definition. There's no apparent change in the UI. Let's go ahead and materialize our asset and see if the asset output is saved to the new location as a CSV file. In the logs, we can see that asset is utilizing the file_io module, which is a good sign. We have implemented the IO manager correctly. And we see the new file path and it is pointing to the correct location, meaning our asset output is saved as a CSV file. We can open the file location, open the file, and view its content to make sure it has valid data. Let's define our second asset. Similar construct, we define a function, and to this function, we provide the name of the function from the first asset. This will define the dependency between the two assets. This function will also return a data frame. We perform few transformations, such as select required columns and rename a column. We will go ahead and return this revised data frame. Let's wrap this function up with the except block. Let's save this and view it in the UI. We see our second asset and there's a dependency between the two. We can materialize the second asset to confirm our transformations are correct. This is one plus point of Dagster. We don't have to run all the steps. If all the assets are materialized and one of them fails or have a code update, then we can fix the error in that asset and rerun from that step forward. If our first asset takes a long time to run, then we can only materialize it once and rerun subsequent assets multiple times. Let's select and materialize our second asset. It ran successfully, and we can view the file to confirm our transformation steps. We have deleted a few columns in this step and renamed a column. All looks good. If you're working with a larger dataset, then you can save your files to Parquet format rather than CSV. This is rather easy. We can change the pandas function from read CSV to read Parquet and to CSV to Parquet. And we need to change the file extension as well. Let's save the updates and head to Dagster UI. We need to reload the asset definition, so we have the updated code. We materialize the assets and see the outcome. In this run instance, we see that our assets are materialized as Parquet files. Let's go ahead and define a second IO manager that will save our asset outputs to a database. This will follow the same construct as our file IO manager. Rather than writing it from scratch, I'll copy paste the pre-written code and we will go over it. We have a class with 3 functions. In the first function, we get a hold of the credentials. In the second function, we handle the asset output. We define the table name with the asset key and save the data frame to a database table with toSQL function. We will skip over the SQL alchemy as we have covered this a number of times on this channel. In the third function, we get a hold of the upstream output and retrieve the asset key. So we want to make sure we pass the correct table name. We query the database table and return it as a data frame. Here we define a decorator of type IO Manager. We pass a dictionary with credentials to this, as we need credentials to connect to the database. In the function, we pass the init context, and using this context, we can retrieve the credentials that we will define next in an env file. We don't want to hardcode the credentials, especially if we check this project in a Git repo. Also, make sure to add the env file to git ignore. Let's quickly define an env file and add our environment variables to it. This file does not have an extension, so make sure to delete the extension if you're creating a new file. So this is the content of env file, and once we reload Dagit, you'll see the environment variable defined here. They'll be loaded to the Dagit UI. Let's go ahead and save the file. We will stop and restart the Dagit UI to pick up this new file. On the restart, we see that it has loaded the environment variables from this file. Now we can implement our database IO Manager. In the asset, change the IO Manager key. I will only change it for the second asset. Now in the init file, we need to first import this IO Manager and then configure it. We provide the key for this IO Manager and then make a call to db IO Manager and invoke the function. Since the function requires a dictionary with credentials, we pass it a dictionary with credentials from the environment variables. Our database IO Manager is implemented. Let's save it and give it a run. As usual, reload all of our asset definition to make sure we have the updated code. Let's go ahead and materialize all of the assets. We can click on the instance to view the run. Our first asset is materialized as a Parquet file, as expected. Let's scroll down and see if the second asset is saved as a database table. Okay, we see a reference to AdventureWorks database and a table name. So this indeed is using our database_IO module. At this point, we can open up our database client. I am using pgadmin for Postgres. We log into our server and expand our database. Under the schema, let's locate the dim_product_category table. We did not specify a schema, so by default, this table will be stored under public schema. We have a dim product category table. Let's query it to validate the expected output. Okay, this looks perfect. Now we can use our IO managers for all the assets and persist them to our desired storage location. Next time we'll cover the S3 storage and how to schedule our assets. This is all on Dagster for now. I hope you enjoyed the session. Like, share, and subscribe. Take care, and I'll see you in the next video.